Hey guys, I thought I'd just do the two problems we did, or we had today in class, to show you, sort of my thoughts on the screencast. Okay, so the first one, I'm actually gonna, do what we did today and start with number 2 with that vector value function, right? And our given, right, was that dx dt was root 1 plus t squared, and dy dt was the natural log of 2 plus t squared. And we were given some other things, like at time t equals 4, we were given some point or something, but we don't care about that right now. So the first part, right, this little gimme here is find the slope of the tangent line at t equals 4. Okay, and we have to think about what this actually means. Right, what is dx dt and dy dt, right? And that's the dx dt is the derivative of the x coordinate with respect to time, which of course is velocity, right? That's velocity, and in the x direction, and dy dt is the velocity in the y direction. And when we try to find the slope of the line tangent to the path of the particle at time t equals 4, right, we're simply looking at how fast is the x changing and how fast is the y changing, right? So we're going to want to look at, right, the change in y over the change in x at that point at t equals 4, right? So usually we might see something like this notationally, right? But we don't need to worry about that, right? But what this really is, right, if we think about what we did last week with polar coordinates, this is dy dt over dx dt evaluated at 4, right? So that's simply ln of 2 plus 16, if I plug in 4, over root 1 plus 16, right? And so that is ln 18 over root 17. And if you punch that into your calculator, I think you get, 0.701. You can always use more than 3 decimal places, but you cannot use fewer on the calculator section, right? So either of those two answers would work, and I would, again, always take the time to say the slope of the tangent line to the path of the particle or something like that, right? To the particle at t equals 4 is whatever this is, 0.701. Okay, so that's sort of the first part. Now let's think about B, which is find the speed of the particle at time t equals 0. T equals 4. And then find the acceleration vector of the particle at time t equals 4. So for the speed, that's looking at the magnitude of the velocity. And the magnitude of the velocity, right, we can sort of think about this as, right, sort of like a Pythagorean theorem, right? If I know dx dt at 4 is root 17 and dy dt at 4 is ln 18, right? That's sort of how fast am I moving in the x, how fast am I moving in the y. So we would take simply the square root of root 17 squared plus ln 18 squared. That whole thing. Notice that's that whole thing squared. It's ln 18 times ln 18, right? Not of ln of 18 squared. It's ln of 18 squared, if that makes sense. You'd punch this into your calculator, right? And I did this on paper, right? So we get just something just over 5. And right, so if we wanted to write a sentence, right, we would write at t equals 4, the speed is this guy. Maybe the speed of the particle, but that's fine. Okay, and then for acceleration at 4, right, we know the velocity vector, right? The velocity vector again is v of t more like we should say, is simply that dx dt, which is root 1 plus t squared, comma dy dt, which is ln 2 plus t squared, right? Those are my, that's sort of how we would parameterize the velocity. It's just from the givens. So the acceleration, then we would just take two derivatives, right? The derivative with respect to t of 1 plus t squared, right, we're going to get a 1/2 down here. I always forget these little brackets. 1/2, and then we're going to get the root 1 plus t squared down here, and then the chain rule, so we're going to get a 2t up there. And then the second guy, we're going to get 1 over 2 plus t squared times 2t, right, because of the derivative, because of the chain rule, right? So we would end up with something like t over 1 plus t squared, comma, 2t over t plus 2 squared, t squared. All right, and that would be my generic guy. And then we would want to do this at 4. So at 4, this guy's really 4 over, what is that, root 17? And this guy is, what is that? That's 8 over 18, right, or 4 over 9, right? So, right, you could put this in decimal form. I don't think you have to simplify either of these guys. You're probably good to go with this. If you wanted to put them into decimal form, it's 0.970, comma 0.444. Okay, again, 3 decimals. That's preferred. Done with part B. Okay. Part C, find the y-coordinate of the particle's position at time t equals 6. Okay, find the y-coordinate. Y-coordinate. We didn't really write a sentence there, right? We would have said acceleration vector at t equals 4, right? We would use, full sentences. The acceleration vector of the particle at t equals 4 is that guy, right? And we would actually write that out again. Okay, so part C, find the y-coordinate of the particle's position at time t equals 6. Okay, so we're looking at position, and again, we want to remind ourselves dy dt was ln of 2 plus t squared, okay? So when we think about where I was, right, in the y direction, if we only think about the y direction, and we know where we were at 4, right? We know y of 4 equals 5 from the given, right? Because we started at 1, 5. So I think you guys should all remember this, right? We have sort of this form, right? Where y of 6 equals y of 4 plus the integral from 4 to 6 of this dy dt. Okay, and let's just think about why that makes sense. Why does that make sense, right? This is the rate that we're changing in the y direction, right? The rate we're moving in the y direction. So, and if we think about that, right, we always said that the area under velocity was equal to the displacement, right? So what this really means is that we could, using our calculator, because we have that here, you can review that. I just posted that onto Canvas. You could take this integral, okay? You could take this definite integral using your calculator, okay? And you will find that y of 6 equals 5, right, from this given up here, plus this integral, which you can find out to be something like 6.571, I think, right? So I would say the y coordinate of the whatever, the particle, right? Because we're boring, right? Much more interesting to use an animal or something. At t equals 6 is, what is that, 11.571. Sounds great. Done. Okay. And then the last guy, which we have not done, I fully acknowledge that, right? We know this formula for sort of the arc length of a parametric curve, right? And we're gonna go over this post mock, but don't worry too much about it, right? It's gonna be the integral from 4 to 6, and then inside the square root we're gonna have dx dt, squared plus dy dt squared. And this should look very much like speed here, very much like speed, which should kind of make sense, right? Instead of thinking about the velocity of our guy, we're going to sort of, we're going to think about that without direction. And we're going to talk, because since we're talking about distance traveled, and we're basically saying that the integral of speed is going to be our distance traveled, right? And so you would plug this in to your calculator, right? I'm forgetting what these things were. What was it? 1 plus root 1 plus t squared? Squared plus ln t 2 plus t squared. You could plug that into your calculator. Maybe you wanted to simplify that a little bit, right? But you'd plug this into your calculator. Turns out you get a point for just getting to here, right? Maybe even a point for here, just knowing that formula. I'm not sure. And you would punch this into your calculator, and you would get this is 12.136, right? So we'd say the total distance traveled by the boring particle from t equals 4 to t equals 6 is 12.136 units, whatever those are. I don't think they were given, but if they were, let's find that. Okay, so we showed our work. Even if we knew to go straight to this formula, right? We showed that we sort of knew where it came from with an integral. Okay, so that was part 2 that we sort of talked about earlier today. I want to talk about one briefly. Okay, one will sort of also set us up nicely for this mock AP. Okay, so one, we're dealing with cars, and I guess the main formula, right? Again, this is a calculator problem. No one's expecting you to look at 450 root sine 0.62t and sort of know what that looks like. If we think about and we're thinking about from 5 to 10 a.m. So that's from t equals 0 to t equals 5 is sort of when we're sketching this out. Okay, and this is the rate at which vehicles arrive at a toll plaza. Okay, so maybe it's morning and there's rush hour or something. And if we think about, this is in radians, right? It's in radians unless you're sort of specified otherwise, right? If you think about 5 times 0.62, that's going to be right around pi, right? Sort of pi in here. So sine of pi, of course, that's where we're going to start going negative. So I think this thing is always positive from t equals 0 to t equals 5. If we're negative, that sort of wouldn't make sense in the context of the problem, right? We don't have negative cars arriving at a toll plaza. Okay, so anyway, part A is asking us, write but don't evaluate. It's funny given that we have a calculator that tells us not to evaluate. An integral expression that gives the total number of vehicles that arrive at the plaza from t equals 1 to t equals 5. So from 6 a.m. to 10 a.m., right? And we can simply say, right, we have the rate at which they arrive. So the number of things that arrive is simply the integral of that rate, right? So this is simply the integral from 1 to 5 of a of t dt, right? That's all that is, right? I even believe you can say this on the AP, right? But we're going to say, we'll actually write this out. Actually write that out and say this, right? So I would incorporate this into a sentence and say the total number of cars that arrive between t equals 1 and t equals 5 is this thing, right? Is this guy 1 to 5 of 450 root sine. That was the most crooked thing I've ever drawn. Let's fix that. That is awful. Okay, there we go. Oops. Too much, though. Too much. Not over the dt, of course. There we go. Okay, is this thing. Okay, and again, we're positive here. So there's nothing scary about anything being negative. There's a train coming by down the hill. All right, so find the average value of the rate in vehicles per hour at which vehicles arrive at the toll plaza from 6 to 10 a.m. Okay, so again, t equals 1 to 5. Okay, and average value of the rate. Okay, if we said, the average rate of change of the rate or something kind of backwards like that, then we'd be talking about something. We're talking the average value of the rate. And again, this function is the rate. It is the rate. So if we're talking about average value, right, the average value is given by, average value is given by 1 over 5 minus 1, right, that's b minus a, times the integral 1 to 5 of this thing, right? So we didn't have to find it in part 1, but we definitely have to use it in part 2, okay? So we have to use the average value formula, and we have to sort of get this, right? So, you would punch this into your calculator. Again, please practice doing that. I posted the things here, and so this is 1/4 of something big, right? And it's actually 375.537, I think. Okay, so they're usually lenient about rounding. If you get 0.537 or 536, I think they'll give you the point either way. It's funny that they're lenient on that. We would write the sentence: the average value for the rate at which cars arrive at the plaza from t equals 1 to t equals 5 is 375.537 cars per hour. Cars per hour. Let's always make sure that we have units there. And we're pretty good, okay? If you do use degree mode, I think you can get points there, okay? So, let's talk about part C here. Okay, so part C, which says, is the rate at which vehicles arrive at the toll plaza at 6 a.m. increasing or decreasing? Increasing or decreasing, okay? So let's, again, think about this. The rate is this thing. A of t equals 450 root sine, what is it, 0.62? 0.62 t. Okay, so you are left with a couple options here, right? What are they, right? You could take the derivative with your calculator. That's probably recommended, okay? We probably want to take the derivative with our calculator, okay, again. So we're looking at a prime of 1, and is that positive? Okay, so you guys could take this derivative by hand if you wanted to, right? It's kind of a messy sort of chain rule thing here, but you certainly could, right? You certainly could. We could do that exercise here because I don't actually have my calculator on me right now, right? But that would be what, 450 times a half times 1 over this thing times the derivative of that thing, which would be cosine 0.62t times 0.62. Right, so that whole thing, you could definitely plug in 1 if you really, really wanted to. Obviously, you're going to need a calculator to get that, right? But at the end of the day, right, you get a of 1 if you use your calculator, and this is like 148.947. So what that tells us, right, is And we need to have that value, and we need to have the sentence here. The sentence for the other guys is still important, right? But the sentence for these guys is, what do we want to say here? I want to say, since a prime of 1 equals 148.947 is greater than 0, the rate at which cars arrive is increasing at t equals 1. Okay? Simple. Okay, make sure we have that sentence, though. That sort of gives us all the credit. Okay, and then part D. A line forms whenever A of t is greater than 400. The number of vehicles in a line is given by this thing. Yikes. This function okay, where A is the time when the line begins to form. To the nearest whole number, find the greatest number of vehicles in line at the toll plaza in the time interval A, or T goes from A up to 4. Okay, so why are we bounded above by 4 and not 5? I don't know, but that's fine, right? We could definitely do that. Okay, so if we're looking for a greatest number of vehicles, right, here is the number of vehicles in the line, right? So we need to consider, to find the maximum, we need to consider n prime of t. N prime of t, and a is just some sort of constant, right? A is just a constant, so we're asking for the derivative of this thing, right? And by the fundamental theorem, right, we would just plug in t, right? There's nothing fancy here, right? We just plug in t for x. We just plug in t for x, and we would get a of t minus 400, right? And we want to know when this is zero. When is this 0? When is n prime of t equal to 0? Well, that's equal to 0 when this is true. When this is true, and you would graph this in your calculator, and you would solve, right? You would solve this thing. You would find the intersection points, right? It's going to have 2. If we think about what a of t looks like, right? It's sort of like a downward facing. It's not parabola, but right, it might as well be. Right. So we're going to find those points. Find points via calc. Again, you guys can do that, right? And we're going to get t is 1.469 or 3.560, we'll say. 3.560. Okay, and those are sort of 2 points that we need to consider, right? That we need to consider where we might have these critical points, right? And then our goal is to sort of look at the boundaries and find out how many cars are in line, right? And so how many cars are in line at we need to consider the boundary points, which are A, which is 1.469, right? That's when the cars first start to form a line, right? We need to consider 3.560, and we need to consider the end 4, right? We need to consider the end 4. Maybe that's when the most cars are in the line, right? So we would simply want to evaluate this guy from A to these other numbers, right? We'll do this guy first. Well, that's really from 1.469 to 1.469 of this a of x minus 400 dx, right? And obviously, if we have, I don't mean this. I mean n of 1.469, right? This first guy, right? This is just going to be 0, right? Because the limits are the same. So that one's kind of easy. My subsequent guys, where I plug in 3.560 and look at the integral from 1.469 to 3.560. This is definitely a calculator exercise. would not recommend this to just, do, but this thing ends up being 71.254. And then the last guy, n of 4, is this integral. Right, sort of saying how many cars are in line, how many cars are in line, right? And that thing ends up being 62.338. So the the biggest number of cars is, of course, this guy, right? So the max number of cars in line from, t equals 1 to 5, is 71 cars, because they said the nearest whole number, right? So that would be the thing we'd want to say. All right, I hope this was helpful. Happy studying for the mock.